Hello friends, welcome back to Synapsara. In our previous videos, we covered two fundamental optimization methods. First, gradient descent. Simple, memory efficient, but painfully slow for ill-conditioned problems. Then Newton's method, amazingly fast, with superlinear convergence, but computationally explosive. Computing and inverting the Hessian is O of n cubed complexity, and storing it requires massive memory. Both methods fail in different ways. Gradient descent is too slow. Newton's method is too expensive. So here's the question. Can we get the best of both worlds? Fast convergence and low memory? The answer is yes. Today we're diving into BFGS, the Broyden-Fletcher-Goldfarb-Shanno algorithm, and its memory-efficient cousin, L-BFGS. These are the algorithms that power modern machine learning. Let's see how they work. Gradient descent is the foundation of optimization. You compute the gradient, take a step in the negative direction. Repeat. Simple, elegant, ubiquitous. But it has fundamental limitations. Watch what happens when we optimize a function with an elongated valley, one where the curvature is drastically different in different directions. Gradient descent zigzags painfully slowly. Why? Because it uses the same step size in all directions. It treats a steep cliff and a gentle slope identically. In narrow valleys, what we call ill-conditioned problems, gradient descent can take tens of thousands of iterations to converge. That's not just slow, it's computationally wasteful. The update rule is simple. X new equals x old minus alpha times the gradient. That alpha, the learning rate, is the same scalar for every dimension. And that's the problem. So what's the alternative? First-order methods like gradient descent use only the gradient, the slope of the function. They're directionally aware but geometrically blind. Second-order methods use both the gradient and the curvature. They ask, how much is this function bending in each direction? Think of three parabolas with different curvatures. The flat one barely curves. You can take large steps safely. The steep one curves sharply. Large steps will overshoot. The curvature tells you how to adapt your step size. This curvature information is captured mathematically by the Hessian matrix, the matrix of all second partial derivatives. It's a symmetric matrix that encodes how the gradient changes as you move in any direction. Here's the problem. Computing the Hessian is expensive. For a function with n variables, that's n squared second derivatives to calculate. And then you have to invert it. That's O of n cubed complexity. For a neural network with 1,000,000 parameters, completely impractical. But let's understand the ideal case first. Newton's method. Newton's method is the gold standard of second-order optimization. The update rule is beautifully simple. X new equals x old minus h, inverse times the gradient. Compare that to gradient descent. Instead of scaling the gradient by a scalar alpha, we are transforming it by the inverse Hessian matrix. This is geometrically profound. H inverse doesn't just scale the step, it rotates and stretches the gradient to align with the function's natural geometry. The advantages are clear. Faster convergence, automatic adaptation to the function's shape, no manual tuning of learning rates. The disadvantages are equally clear. You must compute the Hessian, you must invert it, and for n variables, that's cubic complexity. So here's the question that motivated decades of research. Can we get Newton's speed without Newton's computational cost? Enter BFGS, named after Broyden, Fletcher, Goldfarb, and Shanno, four researchers who independently discovered this algorithm in 1970. The core idea is brilliantly simple. Approximate H inverse iteratively using only gradient information. The update rule looks like Newton's method, x new equals x old minus b, n times the gradient. But Bn is not the true inverse Hessian. It's an approximation that we build up over iterations. How do we update Bn? Here's where it gets mathematical. Define Sn as the step we just took, x new minus x old. Define yn as the change in gradient. Grad f at x new minus grad f at x old. These two vectors contain information about the function's curvature. If the gradient changed a lot, large y sub n, for a small step, small s sub n, that tells us the curvature is high in the direction. The BFGS update formula combines these observations. B new equals B old plus a rank 1 update based on S times S transpose minus another rank 1 update based on B old times Y. Don't panic about the formula. Here's the intuition. Start with B0 as the identity matrix, no curvature information yet. At each iteration, we observe how the position changed, S, and how the gradient changed, Y. We use this to make a rank 2 correction to our approximation. Over iterations, B converges toward the true H inverse. The mathematical beauty is that this update preserves positive definiteness, meaning B always points us downhill, and satisfies the secant equation, which ensures consistency with observed gradient changes. Let me walk you through the complete BFGS algorithm. Initialize. Start at some point x0, set B0 to the identity matrix, then iterate. Step 1, compute the search direction. That's P sub n equals negative B sub n times the gradient. This is our Newton-like direction. Step 2, do a line search to find the optimal step size alpha sub n. We're not just taking a unit step, we're finding how far to go in direction P. Step 3, update position, x new equals x old plus alpha times. Step 4, compute S, the step we took. Step 5, compute Y, the change in gradient. Step 6, update B using the BFGS formula. Step 7, check if we've converged. If not, repeat. Key properties of BFGS. Superlinear convergence. It accelerates as it approaches the optimum. P remains positive definite automatically. No Hessian computation needed. But, and this is crucial, we're storing a full n by n matrix B. That's O of n squared memory. For small problems, say a few hundred variables, this is fine. For modern machine learning with millions of parameters, completely infeasible. This brings us to L-BFGS, limited memory, BFGS. Let's quantify the memory problem. BFGS stores the full matrix B sub n, which has size n by n. For n equals 1 million variables, modest by deep learning standards, B would need 10 to the power 12 floating point numbers. At 8 bytes per number, that's 8 terabytes of memory. Completely impractical. L-BFGS's key insight: don't store B explicitly. Instead, recognize that we don't actually need B. We only need to compute B times the gradient. And we can do that efficiently using only recent history. Store the last m pairs of Sk, Yk. Typically, m is between 3 and 20, much smaller than n. Memory requirement: O of m times n instead of O of n squared. For our million variable problem with m equals 10, that's 10 million numbers or 80 megabytes, 5 orders of magnitude smaller. This is the difference between impossible and trivial. How does L-BFGS compute B times gradient without storing B? Through an elegant algorithm called the two-loop recursion. Input: the current gradient and our stored history of the last m pairs, Sk, Yk. First loop, backward recursion. Start with Q equal to the gradient. For K from most recent to oldest, compute alpha K equals Rho K times Sk transpose times Q update Q, subtract alpha K times K. After this loop, Q has been transformed by implicit information about the curvature. Second loop, forward recursion. Start with R equal to some scaling of Q, often just Q itself. For K from oldest to most recent, compute better equals Rho K times Yk transpose times R, update R, add Sk times the difference, alpha K minus beta. Output, P equals negative R. This is our search direction. This gives us the same direction as if we'd stored B and computed B times gradient, but using only O of m times n operations and memory. The complete L-BFGS algorithm initialize with an empty history buffer. At each iteration, use two-loop recursion to get the search direction. Do line search for step size, update position, compute S and Y. Store this pair in history. If history exceeds M pairs, discard the oldest. Check convergence. So when should you use each method? Gradient descent. Used for very large-scale problems where even OM times N memory is too much. Used for stochastic or online optimization where you're seeing streaming data. Used when you need absolute simplicity and your problem is well-conditioned. BFGS, used for small to medium problems, say up to 1,000 variables. Used when you need fast convergence and memory isn't a constraint. Used for problems where you can afford to store an n-by-n matrix. L-BFGS, used for large-scale problems with thousands to millions of variables. Used when you need fast convergence but memory efficiency matters. This is the workhorse of modern machine learning. In terms of performance, gradient descent has linear convergence but is simple. BFGS has superlinear convergence but poor scalability. L-BFGS has superlinear convergence with excellent scalability. L-BFGS is everywhere in modern computational science. In machine learning, training neural networks, logistic regression, support vector machines. In statistics, maximum likelihood estimation, parameter fitting, Bayesian inference. In science and engineering, molecular dynamics, control systems, signal processing. In finance, portfolio optimization, risk modeling, derivative pricing. Every major scientific computing library implements these algorithms. Thank you so much for watching the video. If you found this helpful, please give it a thumbs up and comment below your questions. Till then, happy optimizing.